Hi, everyone, and welcome to Elektor Engineering Insights. I'm Brian Tristan Williams, and today we're diving into a topic that's increasingly critical in embedded systems, memory-safe programming. Our guest today is Quentin Ochem, Chief Product and Revenue Officer at AdaCore. Hi, Quentin, how are you?
Hi, Brian. I'm good. How are you?
Great, thank you. Thanks for making the time for us on this New York morning where you are. And I see we've got people from all over the world joining us, Hungary, UK, Belgium, and more from the US than we normally get. That must be your influence. Quentin's been with AdaCore for nearly 2 decades and now leads their product strategy and business development. He's been deeply involved in promoting memory-safe languages like Ada, Spark, and Rust, especially in high-integrity systems where reliability really matters. Now, AdaCore is a company known for its work on Ada and Spark, and more recently for collaborating on efforts to bring Rust into safety-critical domains. So we'll talk about the trade-offs between these languages, what's being done to formally verify system safety, and whether the shift away from C and C++ is finally gaining real traction. So if you work in embedded systems, avionics, automotive, or any area where software failure is not an option, you'll want to stick around. Our regular viewers will know we always have a giveaway, so today we're giving away 5 copies of From Rubbing Amber to Swiping Glass, the amazing story of electricity, an illustrated hardcover book from Elektor. It's a beautifully produced collector quality edition that traces the fascinating history of electricity. It's perfect for makers, engineers, and curious minds. Normally sells for €39.95, but 5 lucky viewers will get a copy for free. Stick around for the code word and how to enter. I also want to thank our sponsor that brings you the show for free, BridgeTech. BridgeTech is a global semiconductor company specializing in innovative bridging technologies, including HMI solutions and MCUs. Renowned for the Eve graphic controller ICs, BridgeTech integrates display, audio, and touch into a single chip, reducing development time and cost. They empower engineers with robust, efficient platforms and offer customized hardware and software solutions, including integrated modules for high-performance, compact, and power-efficient electronic designs. For more information, just visit them here at brtchip.com. Now that we've got the housekeeping out of the way, welcome to all our guests who are in the comments section already. To you, Quentin, tell us how you got into the world of programming languages and what drew you to Ada and formal methods in the first place.
So I think I always had an interest in programming languages. I started at university as a software developer, on a software track. And believe it or not, Ada was the first language I was formally taught. I knew C++, C, Java, PHP, those languages before from self-learning. And I was actually quite against the idea of learning Ada at university. Was back in the early 2000s. And at the time, my opinion of it was, why they're teaching me that old language that is only used in rockets and not that useful anymore. And I was blown away by the language when I learned it. I was blown away by the power brought to the ability of adding additional semantic on the execution sequence itself. So in Ada, for example, you don't just have an integer. You have a type that you associate with boundaries and with other properties, and that enables all kinds of checks. And that ends up allowing you to create software that has more meaning embedded to it. It's easier to read, it's easier to understand, and enables all kinds of checks. So that interest in Ada drew me very quickly to AdaCore as a young engineer, where I carry on studying the language, working with the language, and then eventually reaching that position when I'm managing, both the commercial aspect, but also the product strategy and marketing aspects of the company.
Great. And now you've come a long way with AdaCore. You're Chief Product and Revenue Officer.
Yep.
And that's not exactly a technical title. So what does it involve you doing day to day?
So it's a mix, right? We work in a very technical field. So even if you are non-technical occupations, you need to understand some level of the technology. Right now, my job is really a mix. So I am working with the commercial team on commercial opportunities, which tend to be, as I was saying, highly technical. So you really need to understand the specifics of what customers are asking for. I work with the marketing team, which is positioning and explaining and promoting this product. Again, very technical, work. You can't quite explain programming languages and programming tools to people without having some fairly deep understanding on how they work and what they're used for. And also work with the product team, which is creating the roadmap, creating the strategy, creating the positioning of that technology that we have and develop day over day.
Well, I hope you're going to teach me a bit about this, because I'm total newbie to this. I began my embedded journey programming in assembly language on 8051 and also retro computers. Now, at least the 8051 with its Harvard architecture could not read its own code or write to it. But with PCs, and the early PCs at least, they just had full access to the entire memory space, could overwrite each other, could change their own code. And later I learned C and C++, but initially I was stuck with assembly because I didn't trust the compiler to be efficient enough. Those days the chips were not that fast. But I eventually got the hang of C and C++. But these memory-safe languages are becoming more and more popular, so much so that Elektor, as you see there on the screen, we recently hosted a very successful Rust on Embedded conference. And tell me more about why we need Rust as opposed to C, C++.
Yeah, I mean, it's a general question, right? Why do you need to embed in programming language aspect of safety? And that's interesting that you are highlighting a story coming from assembly to C, because if you look at that jump, what you're doing is work on a higher tier formalism that allows you to express safely certain patterns. All of a sudden, you don't have to mess up with registers. You have an assignment operator, and the assignment operator is quote unquote safe, is doing to do what you want it to do, as opposed to maybe messing up the register when you work on the assembler level. And that in that sense, C was a great step forward. It allowed a lot of once we went to the hoop of efficiency, it allowed much safer programming, because a lot of mistakes that you would make in assembly, you would not make anymore in C. The issue is that C and even C++ to a lot of respect try to stay as close as possible to the hardware and try to give you as much control as possible on the system. But the corollary of that, if you have full control by default without really asking for it, then you may misuse it, as they say. With great powers comes great responsibilities. And I think that led us fast forward 40, 50 years down the line at a place where software is ubiquitous. You've got hundreds of thousands of developers with various level of expertise, with various amount of time to work on their software, and the odds of making mistakes with the C formalisms are very, very high. We've known for many years how to avoid those. Like we can think of different programming patterns expanding on the fundamental of C and C++, right? We're still talking about imperative programming. We're still talking about object orientation. We still have subprogram. We still are functions, rather variables, and all of these concepts, right? But there's ways that we know to add on to that, so that by design, some of these mistakes are just absent of the code, as opposed to having to deploy static analysis, testing, and so on and so forth to sort of offset. For us specifically, the family of issues that the language targets are issues related to memory consistency. For example, in Rust, you will ensure so-called memory ownership, making sure that you always have only one reference to a given piece of memory. And if you start to write code that may have two, by default, the compiler will tell you, no, you can have two names that point to this thing. You need to create something different. It will also force you to make sure that if you're using smart pointers, you access value in sort of a exclusive way, and so on and so forth. And all of these capabilities almost eliminates memory issues such as read after free or double free, or this kind of memory inconsistencies that have been endemic in cyber security issues. Of course, the cost of that is that you have to start rethinking the way you architect the software, because things that you could do in C and C++ that were very dangerous potentially now are not possible at all in Rust, at least if you stay within what they call the safe subset of the language. And as a consequence, the way you approach the software programming architecture is a bit different. But one might argue that this different approach is the way you should have thought, from the get-go. So it's not so much something that you didn't have to do before. It's just that the language now is forcing you to do the right thing from the get-go, at least in the case of Rust, with regards to those specific memory consistency issues.
Okay, and you said that you started with Ada at first, and that would be a more mature language. It's been around a while. How long? Yes. How old is Ada?
It's interestingly enough, it's the same age as C++. I think the first C++ standard is 82, 83. That's about the same as Ada. We had 4 or 5 revisions of the Ada language. We now at the 22 revision. So those two languages, in terms of their lifetime, are pretty similar.
And then Rust is seen as a more modern language. Are they competitors, or do they serve different roles?
It's an interesting question. There are situations where you might choose one or the other. So in that sense, you might want to compare them as competitors. But there are also situations where you might feel that one is more adequate. You mentioned that Rust is much more recent, although I think the language has been around for 10 years now. So it's much more recent in a very long time scale, right?
Yeah.
I would say that Rust might be more amenable to people that are accustomed to the IT environment, where Ada and Spark may be more appropriate in environments where you're doing like safety certified embedded or high reliability embedded. But in other places, if you set the Ada level, right, you could choose one or the other and get different benefits, but benefit in both cases.
I see. And Spark is a subset of Ada, is that right?
Spark is a bit of a beast on its own, because it's a fairly large subset of Ada at this stage. We've extended the support for the language quite significantly. But what Spark does, which is quite unique, there's no really any other industrial grade technology out there that does that, is to leverage the Ada language to provide ways to formally verify properties on the source code. And the memory consistency property, if you will, is the first one that Spark proved, and it actually goes way beyond what other languages do. Not only do you have this kind of ownership model, but you can also formally demonstrate absence of division by zero, absence of buffer overflow statically, not through dynamic checks. And beyond that, you can start defining your own properties in the form of Boolean expressions and verify that regardless of how the code is executed, those properties hold. And I want to contrast that with what we know as static analysis. There are a lot of tools. We have some of these tools too at AdaCore that takes arbitrary code and is going to tell you have a bug here, here, and here, which is useful in its own right, in particular from the predicate that you are feeding it pre-existing code. But if you are in the business to go very, very far in terms of integrity, in the business of actually getting guarantees of absence of certain categories of problems, as opposed to merely trying to find potential in the code, then again, you will want to architect and write your code differently and use a different tool set. And that's what Spark is. So Spark will get you to write the code differently with the prover, the verification in the loop, if you will. And if you do that, which goes much further than just the memory ownership constraints, then you would have an extraordinarily strong demonstration of the reliability, the safety, the security of your source code.
And you've spoken about real-world adoption and certification and in Spark. So we could do all kinds of testing, but we usually always miss something in plain testing. What does actual formal verification bring you that you might miss in testing?
So let's look at something simple, right? You have a function that to integer. How many tests do you need to do to exhaustively test that function? It's a very, very large number. That's so large that you can't test that practically. So in testing, you have all kinds of methodologies that will allow you to decide, okay, now I've tested enough. We have structural code coverage, for example. But if you look at structural code coverage, it's an incredibly weak argument if you start to have somewhat complex functions, because you could go to this path, to that path, to this path, and coverage will tell you nothing of the fact that all the possible combinations are actually correct and have been tested. And even in a pure sequential code, you can have values that are problematic, and code coverage will tell nothing about the fact that you've tested enough value. And you have ways to mitigate that to some extent, which things such as boundary value analysis, or maybe you fuzzing and so on and so forth. But still, you will fall short of fully evaluating all the cases, and in 99.99999% of the cases, that might be enough. What Spark would tell you, because it's doing a formal analysis, because it's doing mathematical demonstration of the properties of your code, it will tell you that in 100% of the cases, the source code is correct with regards to its specification. So it's an incredibly stronger argument. Now, in safety, you may or may not want to reach that 100% certainty, because safety is all about odds of failure, right? So maybe the 99.99999% is enough. Maybe it's too expensive to get there. Maybe you want formal proof because you feel like writing all this tests is expensive and writing proof is less expensive, but that's a different trade-off, right? If you go now to the world of security, you want 100% because you're going to have people that are actively looking at exploiting the one mistake that you left in your 10 million lines of code. So for cybersecurity, I would say the argument is somewhat stronger for formal proof than it even is for safety.
Yeah, and like you mentioned, the number of permutations goes up exponentially depending on the complexity of the code.
Yes.
And if I can segue to humans testing and verifying, how about AI? Has that made a big stride in being able to take a good look at your code and identify if there's any problems?
I think it's making progress. I don't have actual stories to share, but intuitively, of course, AI will find its way into this world of static analyzers, in the world of tools that are going to be able to identify bugs for you. And I think that there is a lot of potential in not replacing what we have today with AI, but augmenting it. Right? Okay, I've got the static analysis tool that look at certain bugs. AI will look at others. Maybe AI can explain them better, offer fixes, and so on and so forth. But with AI, you will never get this guarantee of absence of defects, right? You will get help, you will get support, you will get more effective, you will increase throughput of all the activities, but you will still need a tool that has been demonstrated, what we say sound, that is to say that that there is no alarm that is missed by the analysis.
Okay, and if I look at Ada here, bit of sample code that I got on the internet, make it a bit bigger. I've never used it, but I'm seeing it looks a bit like Pascal, it looks a bit like BASIC, and there's a little bit of C structure in there. What was it that you said you loved so much about this language when you first tried it?
I mean, it's not really visible on just a small piece of code like that, because you need to start looking into architecture. You need to start to look at typing or requirements to really get interest in the language. One of the first things that I saw, and this is going to be very basic, but just to illustrate, one of the simplest capabilities is this concept of enumeration in Ada, which was never about giving names to constants. It was always about creating a type that has values that are literal, that have a meaning. There's a successor or predecessor, and they have meanings different from other enumerations. So if I have a color that has red, and if I have light that also has red, those things are different. You can mix them up, you know what they are. Again, types, you can provide ranges. So I can have a type that is percentage and say this goes beyond 0 and 100. And I cannot exceed 100, otherwise it's a mistake, and the compiler or the runtime will check for that. I can create a type that is called miles, and another one that is called kilometers, and make sure that those never get mixed by mistake. So that's the very basic of the language, and then I can start to describe more advanced properties. I could have a sorting function, for example, and describe the expected output. Say, okay, my array is sorted. This is what sorts look like. Please verify that indeed my function is sorting, and I can do that with formal proof automatically. There's a lot that I like also in terms of description of low-level constraints. The language is very extensive, and how you can map registers onto high-level data structures so that you do that mapping once, even to the description of what is the Indianness, right? You can have different Indianness, and then you write your code as if you were accessing a regular structure, and you never have to mess with bitmask or shift or any of these things that are highly error prone. And the list goes on, right? If you give me 5 hours, I will describe those capabilities for 5 hours, but I'd rather stop now and take the next question.
Yeah, let's keep it to under 4 hours.
Okay.
But you mentioned miles and kilometers, and you reminded me, checking for data types like that was a funny story. I'm sure you've got many funny bug stories, but the company I worked for before, they had a website that took payments for movie tickets, and the CVV, the credit card security number, was coded as an integer. And when that was passed on to the credit card company, of course, it was coded in PHP. So if your number starts with a 0, it gets truncated, the 0 gets chopped off, and you're passing a 2-digit to the... So it turned out that for a long time, 10% of the credit card transactions were failing, and we didn't know it. Wow. And we didn't know why until one of our executives happened to have a card with a security code that started with 0, and we tracked down the bug. And those kinds of things with data types, it's incredible the mess you can get yourself into if you're not careful. But regarding that code I showed on screen, I mentioned Pascal. Here's a question from Nigel Benham. And Nigel wants to know if Ada is derived from Pascal, or are these similarities a coincidence?
Ada is heavily inspired from Pascal, absolutely, yes. Pascal was very, very big at the time, and there was a desire from the initial design team to make it very literal, very readable. So they favor this Pascal syntax to like square brackets and other things, which is, there's an argument that can be made in terms of readability, and people that like it very, very much would love to say that it makes things more readable. I think it's a matter of taste, and once you start to using the language, it doesn't really make a difference whether you have a very compact syntax or whether you have more words as in Ada. I mean, programming is not about writing code anymore, right? It's about designing, it's about verifying, it's about and more code is going to be in maintenance than, I mean, the maintenance time is going to be longer than the coding time anyway. It's even more true now with all the code completion engines and soon with AI. But I mean, that's a long answer to the question. Yes, it is related to Pascal at its core.
I thought it looked familiar. I learned a bit of Pascal in the 90s, but it was on PC, and it was quite frustrating that it didn't really have full access to the hardware. I mean, I couldn't even use all the graphics modes, so I gave up on that. But later when I learned C, I went low level with assembly and poking directly into registers, and I could use any graphics mode. So of course that wasn't memory safe programming, that was more hacking. But AdaCore has also been involved in the push for Rust specification, especially around safety certification. What's the goal there, and where does that work stand now?
So if you look at what we like, I mean, yes, we're coming from the Ada programming language. We were founded in 1984 out of an effort to develop an open source compiler, which is now known as GNAT. But really what we care about is safety and security, and that space where we're trying to do better at developing reliable software. And when we saw Rust coming up, the first thing that we identify is that, oh, this is great. There's plenty of great ideas that are coming from this language. Let's see how we can adopt some of those. So this is how, for example, the ownership model was added to Spark, and now there are efforts to add that actually back to the Ada programming language as well. But generally speaking, Rust is a language that has a lot of potential in the safety and reliability space. And if people select that language, we want to be here for them. We want to essentially reproduce the support that we've developed with Ada in terms of toolchains, qualification, certification capabilities, and so on and so forth, to the Rust world. And indeed, one of the first things that you want to look at to enable Rust, actually there are two things that you want to look at to really enable Rust into the embedded world. One is, as you said, safety certification. So we need to be able to provide evidence to authorities of certification bodies that the versions of Rust that we deliver has gone through scrutiny and they're okay to use, they are safe, they are tested, they are properly managed. The other thing that you will need is industrial grade embedded ports. The embedded space is very fragmented. Even today, You've got a lot of different flavors of ARM. You've got RISC-V, you've got x86 embedded systems, and then all the stuff like PowerPC and TriCore that are still around, and many others. You want to have a provider that gives you a toolchain for your specific target on your specific OS that has been tested for industrial purposes. And that's the other edge of what we're doing. Our goal is to get support parity between Rust and ADA and Spark as part of our portfolio. Now there's a long road to get there, but that's our objective. So that I have to do this quick segue here. I've been working for AdaCore for 20 years. I have never once convinced anybody to use Ada, and believe me, I tried. And I think that that process of deciding on which language is something that really you need to do as a developer. And I can provide information for you to base your decision upon. And once you engage on a path, I can support that. But I cannot quite convince you, if you're not already on that path, to use anything. So if you're on the path of selecting Rust, this is awesome because Rust is so much safer, it's so much better than the alternatives out there, such as C and C++. And us at AdaCore, we want to be able to support you in that case in the same way we've been supporting you for Ada and Spark.
There's a question here about the overhead. What amount of overhead has Ada and Rust compared to C or C++? It's
negligible. Actually, there are some places where Ada and Rust perform better than C and C++. Somewhere they're not. As every language, there are gotcha. So if you're using something that is highly inefficient, you're going to lose. But Ada, Rust, C, and C++ are languages that are compiled directly to the hardware. There's no virtual machine. There's no garbage collector. So and we're using the same compilers, right? In the case of Rust, it's LLVM. In the case of Ada, we have both LLVM and GCC, which are obviously available for C and C++. So we find that if you look at skilled developers that masters the technology, there's no overhead. You will find studies out there where you see, okay, C is 100% and Rust is 102 and Ada is 120 and so on and so forth. But they are showing different ways of using the language, and maybe there's this feature that you should not be using in Ada if you're looking at performance and vice versa. But overall, you should expect similar overhead, which make them great for embedded. I mean, Nvidia is using that in firmware, which is extraordinarily constraining in terms of memory and time, right? And it worked just fine.
Tell me more about Nvidia, speaking of a segue. What's your partnership with them about?
So they came to us about 8-10 years ago, and they were interested to look at changing their development methodologies for firmware where security and safety was paramount. They looked at the amount of work it was going to go there with C, and that requires a lot of coding standard, a lot of verification, a lot of reviews, and even with all of that, you know that in particular in security, as we said, you're going to miss some mistakes. And they looked at Spark and Ada not so much as a shift of language. Actually, what they told us is that we don't care about another programming language. We're in the valley. One of those is getting popped every week, so let's not consider that. But they look at Spark as a different way to develop software. Because when you do formal proof, you need to constantly verify. You need to constantly check the prover to reach that grade. And that was the inception. Like, they found that by using formal proof, by using Spark, they ended up with code with a much smaller defect rate. So there are a couple of presentations out there that you can find. I think it's Black Hat at DEF CON where they describe that. So they started to deploy it on pieces of firmware where it was very critical not to have mistakes. And then our relationship evolved more recently with the DriveOS Auto team that was interested to using Spark also, but in the context of some of the automotive software that is being developed. So much so that we jointly published an ISO 26262 development process for ISILD safety certified code with Spark, which I find quite unique. I mean, I don't know of any other company in the world that have published their safety development process for ISO, and they tend to see that as their secret sauce. The fact that Nvidia was willing to open source that for everybody to see, to use, I think is quite remarkable. And the fact that on top of that, this is the Spark reference process. It's really a foundational document on how to use the language and how to use formal method to reach the highest level of confidence in an automotive concept.
And the ISO, just Googling it here for our audience, ISO 26262 is an international standard for functional safety of electrical and electronic systems in road vehicles. So yes, that is very interesting that it is published that way. And I think if you can't get someone to use a language, if you can't encourage them, it's usually not the language is bad. It's just so many languages, there are too many, I think. What's your opinion?
In the world where we operate as AdaCore, there's only really 3 or 4 options depending on how you count, right? I think you have C and C++, which you may count as 1 or 2 depending on who you are. We tend to count that as 1, but I know C++ people get very upset when we do that. So let's say 2. Because you need efficiency, you need the plethora of targets, you need availability of support from tools and so on and so forth. You have Ada and Spark, which again you may count as 1 or 2. And then you have Rust. I don't think that in that world of embedded, you have many different options. Now, if you look at the software market at large, I think that one size doesn't fit it all. And you could, but I wouldn't use Ada to write a web server, for example. I think that wouldn't be a good use of the language. I think that all the technology are out there. So yes, there are a lot of languages, but you tend to have applications for them that make sense. Python is a fantastic language for prototyping, for scripting. And I wouldn't use Ada either, nor C actually, or even Rust for those things. And so, yes, there are many languages. Yes, there may be a little bit too many because it's also fun to write a new language. People like to do that. But I think that if you look at the credible alternative out there per application domain, you'll find that the number is just right. And it's important to have alternatives because that creates a bit of competition, that creates a bit of wake-up calls, that pushes the industry forward. To a large respect, Rust helped Ada a lot because it made us realize that there were aspects of safety that we did not cover with the Ada Spark technology and that were needed to be covered. And I'm sure that people that are doing Rust or even C and C++ are inspired by other languages and helping develop them through.
Well, that's a good point. Question from Only Good on YouTube. It's in terms of safety, performance, and systems programming, what are some things that Ada can do and Rust cannot, and vice versa?
So we're not talking about Spark now. We're talking about Ada specifically. So right now, Ada doesn't have a memory ownership model. You need Spark with formal proof for that. So this is something that you get natively with Rust. I would say that's the biggest thing on that end. On the other end, Ada allows you to put a lot of information in the specification and the architecture of the application, right? So Rust talking about types, Boolean constraints, and so on and so forth. This is something that Rust doesn't have. Rust has typing that allows you to say this is int32 but you cannot say this is miles, this is a kilometer, and they don't match. So I would say that those are the biggest areas. There's a blog post that I wrote on our blog if you want to see which tackles specifically that question, like what can you do with Ada, with Rust and Spark, and which one should I choose? And there's no easy answer. In terms of systems programming and performance-wise, I think there could be the tie. Like they are both system-level languages. They're both very efficient. You won't have bottlenecks because you're using one of the other language. For systems programming, I would tend to say that, like by system programming, I mean low level, like when you start to need to have access to registers, when you start to embed low level, maybe a bit of assembly in your code. With Ada, you have a lot of semantics around data mapping, which may be a bit ahead, but with Rust you would do the traditional mask. So it would be a bit less safe in that regard, if you will. But I don't think that there is something that you would be able, like some need that you will not be able to carry with one language or the other. I mean, Rust has this unsafe section that allows you to get dirty when you need to get dirty. And there are similar provision in Ada when you really need to get your hands dirty. The difference with C and C++ is that with C and C++, it's kind of the default to be able to do very low level and dangerous things. With Ada, Spark, and Rust, you need to create very specific section of the code or use very specific constructions that says, okay, all bets are off. I know what I'm doing here, but that's very, very visible.
Great. And I've pulled up your blog now that you mentioned it. It's at blog.adacore.com/author/Ochem. That's Ochem.
And I think yeah, that's the one.
The second blog post, is this the one you're talking about?
Yes.
Ada, Spark, or Rust over C++. I would encourage the audience to check that out. But I am interested in the 7 differences in Ada blog post as well. Carry on.
Yeah, no, that's about enhancement to the language that we're working on now. So we're showing all the new features that we are developing for the language.
Yeah, and like I say, there's so many languages and nobody has time to learn them all. And I I stick with what works, and then I end up using a language that has long past obsolete.
Mm-hmm.
So what I've found, I'm still new at Python, but ChatGPT and Claude have helped me a lot to figure out how to get things working. What I found with Python is that the amount of code that you need to achieve something is typically always very small because there's so many libraries available and extensions and open source community. How does that compare in, say, Ada and Rust?
So we need to look at the kind of application that you would want to write, which again links to the one size doesn't fit it all aspect. If you are developing high integrity software on embedded devices, or even native, but like you have a simulator for, I don't know, a fighter, or you have a server, application that you really need to master the entire code, the amount of libraries, regardless of the language, is going to be small, because the thing that you can trust, there aren't that many out there, and that's true for all the languages. Python, you wouldn't use in those situations, right? So it's kind of out.
Yeah.
If you go as far as we have customers using bare metal environments, so they're not even using an OS, like they do everything. Now, if you're looking at more general programming, where all of a sudden you have access to, like PC programming, for example, you have access to all of these environments. Nothing can beat Python, obviously. Rust has a fairly extensive environment and community, so you will find the vast majority of what you need. More likely you will get it. Ada and Spark is a bit more narrow in that regard. I mean, we do have a package manager. It's called Alir, similar to Cargo, which has something and is growing. But it's likely that at some point you will need to interface with an existing C library. Now, thankfully, there are a lot of capacities that are embedded in the Ada language to interface with pre-existing libraries. But it's likely that this is something that you will want to do.
Yeah. And in terms of C++ and moving to Python, see, Nvidia, heavily involved in machine learning, they decided not to head toward Python, but they deliberately chose to replace C and C++ with Spark Ada. And somehow you've claimed that they achieve mathematical assurance of 0 runtime errors in critical firmware components. How is that possible?
So I'm not sure I understand the question, actually. What do you mean by how is that possible?
Well, we mentioned earlier the number of permutations when checking systems, like even 64 bits in 8x8 grid will give you 18 quintillion combinations that you couldn't possibly run through. So how do you get the assurance that mathematically 100% that you don't have runtime errors?
So you're going to use theorem proving capabilities. Like we have things such as SAT solvers or SMT solvers that are tools that can reason formally. So if you look at an integer, you don't have X number of permutations. You have a formally defined integer on which comes with properties, and you apply operation, and every time you operate operations, You generate conditions that are necessary to meet for said operation to be correct. So for example, let's say you have two integers, one 16 bits and one 32 bit, and you do an assignment from 32 bit to 16 bit. You generate a condition that says, hey, that source integers needs to be within those boundaries. Otherwise, the value that you have won't fit in 16 bit and you'll have an issue. Of course, we'll do something, God knows what, but in Spark, you generate a condition. And then the two reasons say, is there a possibility for that condition to be broken? And for example, yes, you could have more value than you want, but just before you have an if statement that say, if my value is below 100 and above minus 100. And then the prover says, oh, well, now I know that I got this constraint that was added to my corpus of reasoning that constrains the value of that specific variable to be within that very, very small range. So I know that my verification condition cannot be broken because, of course, this small range is within the 16 bits range that I wanted initially. And you can imagine the plethora of conditions that get generated all over the place. Like I've just described a very simple one, but you have a lot more like that. And the place we're in right now is that the technology has evolved so much that is able to handle thousands and thousands of these things in a very effective way.
Great. And I'm sorry if I make you repeat yourself because there is still a bit of unclarity. For example, Nigel is asking if Spark verification is part of the compilation or is a separate tool. If I can just take it from a completely new guy here, as I understand it, Rust and Ada are independent languages, standalone. Rust is more modern, Ada is mature, and Spark is like a subset of Ada with more restricted features.
Yes. So what we remove from Ada to get to Spark are features that makes the proof impossible. There aren't that many anymore. Like we used to remove exceptions, but now we support exceptions. We used to remove pointers, but now we support pointers. So you have almost the entirety of the language available. But yes, indeed, that's a very good question, Nigel. The proof is separate from the compilation. So compilation will give you the Ada value. There's a lot of checks that you get there already, the simple stuff, a bit like Rust in that regard. And then Spark is a separate process akin to static analysis that will reason on the code. And typically this reasoning can take longer than compilation. So you don't want that reasoning to be in the way of efficiently compiling code.
Okay. And here's an off-topic question, but Oligood wants to know if you're a French speaker.
I'm trying to hide that, but I fail. So indeed, and a good spot. I am a French.
Okay, and it's been what you said 10 years now for Rust. How widespread is it in industry, in use? Because I've never actually seen it in use. Maybe I've got blinders on.
Oh yeah, no, a lot of people have adopted Rust in various different places. I think there's some Linux kernel PCs that are now written in Rust. Microsoft has adopted Rust. In the IT world, there's a very significant track record. It's a very popular and successful language. In the embedded world, in particular, the high integrity embedded world that we're talking about, it's the beginning, and it's the beginning because you need to have certification, you need to have toolchain, you need to have industrial support, and maybe people tend to be more conservative in language switches in this area because the cost of developing software is very, very high, and you don't tend to write software or throw it out, and that's another thing, right? Whilst in some situations in the IT world, it's okay to rewrite from scratch. In our world, in the world where AdaCore operates, you never write from scratch. So even if you're looking at Nvidia, but that's true for all of our customers, they didn't replace C and C++ by Ada Spark. They started to adopt Ada and Spark, and they select the pieces of software that are relevant for either these new modules or last translation, but that integrates into a larger body of source code that is still developed in other languages. So that pace, Rust is going to see these same changes.
Well, it certainly is picking up pace, but there's a lot of people who still rely on C and C++ for safety critical applications. Is that just slow moving?
You can write extraordinary safe code in C and C++. People have done that for decades. So there's no problem here per se, and people will continue to do that for the decades to come. I don't see C and C++ being, ditched anytime in my lifetime, at least. But the issue is that, what do you put your trade-off? Do you want to spend a lot of efforts testing, doing static analysis, doing code review, and still having some risk post-deployment, at integration time, or in the field? How do you manage those risks? Is that the trade-off that you want? Is that the how you want to handle your software? But then the advantage of that is that it's there, it's known, you don't have to change anything, you don't have to train people, you don't have to change your hiring process, you don't have to change your development process. Or do you feel like it's worthwhile doing upfront investments, changing methodologies, training people, changing toolshed, so that you're getting benefits later in the process? And those two answers, depending on the context, one may be that both could be correct. We've seen mandates from the US government in the previous legislature that asked software developer to use memory safe languages and for cybersecurity, right? But I think that people are also going to get better at spotting issues in C, even if it's never going to be perfect. And in many situations, maybe that's good enough.
And do you ever see Ada, Spark, and Rust work together in a mixed code-based project, or is that asking for trouble?
No, it's Ada, Spark, C, and C++. That's a daily activity. Like Ada and Spark, these days, even for people that have been using the technology for decades, is almost always interfaced to some respect with C and C++. And the language is made for that. Like, we have provision for that, and you know that when you go, you lose guarantees when you cross the boundaries of the language, but that's okay. Like, this is well identified. Rust and C, same story. You have pre-existing components. You want to integrate with pre-existing components. Of course, you're going to interface. The three languages together, I have not seen yet. But there's no reason for that to happen. As a matter of fact, at AdaCore, we're working on technology that will help generating automatic bindings between those languages, so that you get some level of automatism, some level of guarantees at when crossing the boundaries of the language.
Okay. Before I move on to the next question, as promised for our audience, the competition code word is the URL, but we'll also drop it in the chat. And we're giving away 5 copies of From Rubbing Amber to Swiping Glass from our own Clemens Farlands at Elektor. And the code word I've chosen, since Quentin is talking about safe code word we'll use today is safe. So head over to that page, enter the competition, and good luck. Onto open source, I wanted to ask you, do you see a lot of open source in Ada, or is it mostly still commercial?
There's quite a bit. If you look at GitHub, I mean, you need to, if you compare with Python, it's going to be ridiculously small, of course. But there are quite a few projects on GitHub, particularly on open source Ada and Spark. We have this Alir package manager that charters a bit this space. The compiler itself is open source. We open source of our libraries. So I think that there's a decent amount out there available, yes.
Cool. And here's a comment from a LinkedIn user. Rust is also intensively used in embedded software engineering education. So I would ask you, if you were designing a curriculum for embedded software today, what language would you start with? I
would definitely teach the 3 languages, C++, Ada, Spark, and Rust. I think that it's important. As a software engineer, it's important. I care about languages, of course, and I care about Ada because that's my trade, that's my training. But I think that as a software engineer, you need to be very eclectic in your way you approach languages. You need to understand different things. It helps, you understand C better if you know Ada. You understand Rust better if you know C, right? And then that gets you into a place where you can decide which tool you're going to use for which purpose and why, as opposed to some of the almost religious decisions that you see made sometimes, where people are, okay, I'm only going to program in C or C++, or I'm only going to program in Rust because that's that's what I love, which is almost always the wrong approach.
And do you see a lot of misconceptions about safe languages?
Yes.
What sort of misconceptions do you run across?
I mean, the fact that in terms of cost in particular, they're equivalent. Like a lot of people don't see the value because they never experienced it. Don't see the value in having languages that clear out issues from the get-go as you write and design code. And a lot of people believe that, hey, you can do anything for C. I can have my C safe just as much as other languages. And there's an overconfidence in, which I don't share. Like, I'm very anxious whenever I program, but a lot of programmers are very confident in either their ability or their team's ability. And then, individually they may be right, but once you start to have larger teams of, dozens of hundreds of people, or if you have software that's going to survive through decades, so generations of developer, you can't have that confidence anymore because you don't know what other people are going to do. You don't know what's going to happen in 10 years. So you need to start thinking in terms of how do I guarantee that things endure the test of time and the scale at which they need to operate.
Yeah, and it is safety critical applications like aviation, autonomous vehicles, robotics. It's not an MP3 player, so you have to work hard on safety. And you've said C++, you can write safe codes, and you've said it's not going away in your lifetime, but you think it will still dominate in 5 years in security critical applications?
In 5 years, yes. Given the sheer amount of installed code base, I wouldn't bet on C++ losing number one in 5 years. Now, I would definitely hope that the trend is downward, that we reduce the amount of C++. I mean, now, not as a software developer, now, but as a user, I would like the systems that I'm using to rely less on C++ and more on Ada and Spark, because I've studied how hard it is to ensure that the development that you do in C++ is exempt or mitigates errors.
Okay, and you're not really seeing a pathway in for Python into security critical?
Not in there, but it's even in the security critical world. There's a lot that is missing in Python to make it a safety critical language. Absolutely.
Well, Jan Willem wants to know, seeing that I can't use Rust in some of my embedded projects, and I personally I'd like to know why you can't use Rust, but assuming that's the case, and similarly Ada, what would need to change to help improve application opportunities and adoption rates?
So like you, it's difficult to answer without knowing why. At AdaCore, we do a lot of advocacy. We first of all, we're making sure that, I don't know if that's a target availability issue, like do you have the compiler for your actual target, but we're working a lot in making sure that all targets that are needed by our customer or potential customer are available, that they come with the right pedigree, certification, instrument grade testing, and so on and so forth. We're working a lot with universities. You are mentioning the fact that Rust is taught at the embedded program, but we work with a number of people that are teaching Ada and Spark for the same purposes. And I think we just need to communicate about the options, technical options, in a way that is not idiosyncratic, which is why I've tried to do, I don't know how much I succeeded, but which is why I've tried to do in that blog post, say, hey, these are the alternatives, this is what they mean. Let's look at that pragmatically.
Okay,
So
Jan Willem says it was indeed lack of compilers that was the problem.
May I ask what targets you have?
Yeah, Jan Willem, let us know what embedded system you're targeting. And now, we thought we were using formal methods. We were taught to program formally. How would you describe this term formal methods as it applies to safe languages?
So it's a superset. It's something that you put on top. You need to have the memory safe language as a foundation, or the safe language as the foundation of what you're doing. And then if that language can enable formal method, that is to say you have an unambiguous language, well-defined, that allows you to express the kind of properties that you need to verify, then you would go one step further and enable formal methods on top of it, which is going to give you those incredible guarantees in terms of safety and security.
Great, thanks. Somebody, John Cassie, regarding what languages to teach for an embedded developer, AdaCore.com/books has some very useful books. LinkedIn has done a bit of censorship there. I'm not sure what that for the developer like Ada or embedded C developer, or Spark Ada for the Misra C developer. I'd hope they add some books regarding Rust for the developer. These books help understand the trade-offs between the language and why the decisions were made for that language. And yes, indeed, we also got a Rust course at Elektor, but what sort of learning materials do you have at AdaCore?
So we have an open platform called learn.adacore.com, which you can just get and learn the language by yourself. A couple of books. I wrote one in my young years, also showing Ada for C++ and Java developers. And perhaps even more interestingly, we also publish all of our professional training courses on GitHub. So you have access to the source material, it's open source, you're free to study it, you're free to use it if you'd like to teach Ada. And nowadays, with the addition of AI like Claude or ChatGPT, I think that you have all the tools that you need to learn the language really.
That's a very neat website, actually. It looks like something you'd want to get into. It's nice and tidy. It looks very different to, say, the PHP website, which has looked 20 years old for 20 years. But you do have to maintain old code. People are still maintaining COBOL code bases.
Oh, yes. Yeah.
Which does make life difficult when you want to be secure and you're maintaining legacy code.
Mm-hmm.
We've got a couple minutes left. Just to go back to Jan Willem, you asked what target. He says ESP32 now has support for Rust, but not Ada, he thinks.
So it's an interesting one. We don't have a compiler for ESP32. I can't recall if GCC has an open source backend. If it did, it wouldn't be a big task to port our GNAT compiler to ESP32. That's part of the stuff that we do for our customers. The last alternative that you have for Ada specifically is that we have an Ada to C compiler. So I want to be a bit careful here. There's not a translator from Ada to C in a way that the C that you get is maintainable or anything like that. But if you consider C as sort of an intermediate representation in compilation chain, you can plug the GNAT compiler with your C compiler. And then if you consider that this plug is one compiler, then you can target anything that you have a C compiler for. And if you are interested into exploring that possibility, send us an email and we can talk.
Yeah, what email address could we use?
Ochem@adacore.com, I guess at this stage, since I'm the one speaking, I'll be happy to direct you to the right people that will follow up.
I have dropped that into the chat on the various platforms, so I hope you don't get too much spam from that. But with that, I would like to thank you very much for taking the time to be with us, Quentin Ochem from AdaCore. Thank you for your time today.
Thank you. Thanks, Brian. Thanks, everyone.
It was very illuminating, and it clarified to me the differences between Rust and Ada, and Spark as part of Ada. So thanks for that. Thanks for teaching me. Thanks for teaching our audience. Jan Willem's final comment sounds very interesting. Thanks. So good luck on getting that to work, Jan. And that's all for this episode of Elektor Engineering Insights. Big thanks to Quentin Ochem, yes, French, for joining us and sharing his insights on memory-safe programming and the future of embedded development. Thanks for watching. Don't forget to like and subscribe, whatever platform you're on, and share if you found this valuable. Good luck to those of you entering the competition. The word, again, is SAFE, S-A-F-E. It's right up Quentin's alley. And thank you very much, and goodbye.